A lot of our focus so far in physics, when we've looked at motion, has been on uniform motion. That is, motion with constant velocity. So we have formulas for calculating the velocity of an object if its velocity is constant, or a formula for calculating the speed of an object if its speed is constant. But that's not always the case. There are plenty of situations where objects move in a way where their velocity changes. In other words, in a way where they accelerate. So when an object accelerates, asking what its velocity is suddenly not such a simple question, because it's not just one number. It's a bunch of different numbers, and it's always changing. So I'd like to get to the point in this lesson where we can kind of ask those questions. When we have an object that's accelerating, we can say, okay, what is its velocity at this particular time, and at this particular time, and at this particular time? So the one requirement we're going to have in order for today's tricks to work is that even though the object is allowed to not have constant velocity, it needs to be moving with constant acceleration. In other words, it needs to accelerate uniformly. And this style of problem, or this topic, is sometimes called uniform accelerated motion, or UAM. So when an object has constant acceleration, there are a few things we might ask about that object. I've already talked about how the velocity will be changing, so we might ask, what was its velocity to begin with? And what is its velocity now? We could call those VF and VI, the final velocity and the initial velocity. If it has a constant acceleration, one of the things we could ask about it is, what is its acceleration? This object is clearly moving. How much did it move? How far did it go? What is its displacement? And the other thing that kind of is tied into all this is how much time this all took. If this is its initial velocity and this is its final velocity, how long did it take to go from this velocity to this velocity? Or if this is the displacement of the object, the straight arrow from where it started to where it finished, how long did it take to cover this displacement? So the last thing we might ask about is delta t. So final velocity, initial velocity, acceleration, displacement, and change in time. Those are sort of the 5 things we might ask about an object that has constant acceleration. So let's look at these. I've sort of grouped them a little bit here. These first 4 are all vectors. That's why I put vector hats on them. And because they're vectors, that means they have a direction. So what that means for us is that when we're working with these quantities in formulas in our calculator, we need to pay close attention to if these numbers are positive or negative, because that's how we communicate direction. Delta t, which actually we're going to start writing as just plain old t. When you see me write this in the formulas coming up down here, I don't mean something different than delta t. I still mean delta t. We're just dropping the delta as a way to kind of clean the formulas up and make them a little bit less cluttered. So when you see this sort of from now on in this lesson, I do mean this, delta t. It's just a short way of writing it. Anyways, this guy in this group of 5 quantities is our sole scalar. This does not have a direction, so we do not have to think about whether it's positive or negative. It'll always just be a positive number. So what are some formulas that link these 5 things together? The idea here is we're going to be able to solve problems where if you know some of these things, you'll be able to find some of the others. Well, the first formula is this. VF equals VI plus AT. So that kind of says if I'm looking at, if I have an object that's accelerating for a period of time, it has a speed at the beginning and a speed at the end. And if it starts really fast, it might be able to achieve a higher speed at the end. If it accelerates really hard, that'll help it achieve a higher speed at the end. And if the more time it accelerates for, will help it achieve a higher speed at the end. All that stuff makes sort of intuitive sense. When I write these equations down, I like to just make sure that some of the order of things and the places they appeared in the equation kind of make sense with my intuition. The next equation is D equals VI T plus 1/2 A T squared. So this equation for displacement, we can think of this for now, if we're not being too particular, as how far an object goes. We see that the faster an object starting speed, the further it'll be able to go. The longer it travels for, the further it'll be able to go. And the higher its acceleration while it's moving, the further it'll be able to go. That all makes a bit of sense. And then our last formula is, the last one of the big 3, VF squared equals VI squared plus 2AD. So this formula tells us about the final speed of an object, right? Velocity technically, but if we're just kind of talking about the intuition we get from this, we can think of this as speed temporarily. So the faster I start going, the higher the speed I might be able to achieve at the end. If you're going faster to begin with, it's easier to hit a high top speed. Also, the more I accelerate, and the more distance I have to accelerate in, the higher my top speed will be. That all makes sense. So, these 3 equations are really powerful. We will use these a lot in this course. And all of them relate these variables here to each other. So if I know some of these and I want to find some other ones, these equations are where it's at. So let's try a couple of examples with them. Example 1. A police car traveling at 80 kilometers an hour east speeds up to 100 kilometers an hour east in 1.7 seconds. What is its acceleration? So right off the bat here, I see these numbers are in kilometers per hour. That's not metric base units, so I'm going to convert those to meters per second right away. So I'll use my shortcut here. Divide this guy by 3.6, and that gives me 22.222 meters per second. And this guy, divided by 3.6, equals 27.778 meters per second. I'm including 5 sig figs here and here, just to include a bit more extra than I want. Again, my final answer I'm going to leave in 3 sig figs. That's sort of standard for what I kind of like from my students, is 3 sig figs in your final answer. So we'll keep 5 as we're going through the question. Okay, so now these guys are in metric base units. This guy is already in metric base units. Let's see if we can tackle this problem. And the way I like to start all these problems is by writing down all of these quantities here. Filling in what I know, identifying what I don't, and that helps me kind of coordinate a plan of attack. So, VF, VI, A, D, and T. Okay. The police car is traveling at 80, and then it speeds up to 100. So my initial speed is going to be the 80, or the 22.222. My final speed at the end of this acceleration is 100, or 27.778. And since these guys both have vector hats, direction is important. I gotta think, are these positive or negative numbers? Well, I think we can assume that in both of these situations, the police car is traveling forward. So I would call these both positive. I'll squeeze in some positive signs here for both of them. Okay. To go from here to here, from this initial velocity to this final velocity, takes 1.7 seconds. So that's our time. And we are trying to find the acceleration. So I'm going to put a big question mark beside acceleration. And you'll notice that D is kind of sitting here by itself. We don't really know what's going to go in there, but we're not also really looking for what's there. So let's now look at our three kinematics equations, the big three, as we've been calling them. If I want to solve this problem, I need a formula with A in it, because that'll help me solve for A. But if that formula that I pick has D in it, then I'm going to have to plug in something for D, and I won't know what to plug in. So I want to avoid that. I'm looking for a formula that has A, but not D. And if we look up here at our options, we see there's only one formula that fits the bill, and it's this guy. This guy has A, and there's no D in it anywhere. So let's write down that formula, and we'll go from there. VF equals VI plus AT. I'm looking for A, so I'm going to isolate A, get A on one side of this equation all by itself. And if I do that, I'm going to get VF minus VI over T equals A. And so now to find A, I just got to plug numbers in over here. So this is my 27.778, this is my 22.222, and this is my 1.7. And if I plug that all in, I get, let's see, if I round to 3 sig figs, I get 3.27. Notably, I get positive 3.27. Since the thing I'm looking for, A, is a vector, I need to pay attention to whether it is positive or negative. So, again, because I put metric base units into my formulas for everything, I know I'm going to get metric base units out. So this 3.27 is in the metric base units of acceleration, so meters per second squared. And this positive means the direction of the acceleration is forwards. 3.27 meters per second squared forward. Perfect. Okay, let's look at one more. Okay, in this one I'm going to draw a bit of a diagram. Probably could have done that in the last one, actually. It's certainly good practice. Here in particular, I think it'll help a bit. So a sprinter, 20 meters before the finish line, finds a little extra energy in her legs and accelerates at 0.9 meters per second squared for the rest of the race. She crosses the finish line going 9.3 meters per second. What was her velocity when she started accelerating? So I've got a race going. Here's my start line, let's say. And here's my finish line, let's say. And my sprinter, a little bit before the finish line, 20 meters before the finish, maybe the sprinter's over here, is running hard. And at this point, finds a little extra energy and she starts to accelerate. So, during this period of time from here to here, she has an acceleration of 0.9 meters per second squared. And she's moving forwards and speeding up. If you're moving forwards and speeding up, that means your acceleration would be forwards too. So the acceleration is positive. And she is 20 meters away from the finish line, so we can kind of draw that in too. And when she gets to the finish line, over here she is. Crossing the finish line. She's moving at 9.3 meters per second. Okay. Now, one thing I find really important in a lot of these questions is to be very explicit with yourself about where is initial and where is final. Where are you saying this problem starts and where are you saying the problem ends? Where are you starting your stopwatch and where are you ending your stopwatch? Because in this problem, there's a few different options. A lot of people might say, oh, well, initial should be the start of the race. So they'll call initial here. But there's not much going on during this first part. All the action is over here. This is where we know the displacement. This is where we know the acceleration. So I think for this question, we're going to actually say this point over here, where she starts accelerating 20 meters from the finish. This is initial. That's where I'm going to start my stopwatch. And this, when she crosses the finish line, is going to be final. So that means when I measure time, it's going to be the time from here to here. When I measure displacement, it's going to be the displacement from here to here. When I talk about initial velocity, it's the velocity here. When I talk about the final velocity, it's the velocity here. So where you pick initial and final to be affects everything else in the problem. That's why it's really important to be quite clear with yourself about that first. Otherwise, I find if students don't write this down, they'll say like, initial velocity is 0 because they are thinking initial is over here, and when you start the race, you're probably not moving, and then they'll use 20 meters, the distance from here to here, for their D, So they're kind of all over the place. You got to be clear with yourself. Where's initial? Where's final? And then you know that delta t is going to be from initial to final. D, the displacement, is from initial to final. And this is where your VI is, and this is where your VF is. So now that we've been clear about that, let's go about solving this. So again, we write down the 5 things: VF, VI, A, D, T. So I know VF, final velocity, is positive 9.3. I know VI, the initial velocity, oh, I don't know that. In fact, that is what we're looking for. Her velocity when she started accelerating. I know A, between initial and final during this time period that we're looking at, is positive 0.9. I know the displacement, a straight arrow from start to finish, from initial to final, is 20 meters, and it's going to the right. She starts here, she ends here, so my arrow is going that way. And the time it takes to go from here to here, I have no idea, so I'm going to leave this blank. That means I'll be looking for a formula that has VI and doesn't have T. And if we look back up at our options, we see there's one that fits the bill, and it's this guy. VF squared equals VI squared plus 2AD. And we're going to try and solve this guy for VI. So I'm going to move this stuff to the other side. It gives me VF squared minus 2AD equals VI squared. And then I'm going to have to take the square root of both sides to get VI all by itself. And remember, whenever I take the square root in order to get rid of a square, it can be plus or minus. So here I'm taking the square root to get rid of this square. So when I do that on this side, I have to remember that the answer can be plus or minus. So I'm just going to rewrite this the other way around. I'll swap the left and the right side. We're always allowed to do that just because it looks a bit cleaner, I think, when the thing I'm looking for is on the left. So VF is positive 9.3, and that's going to be squared. A is positive 0.9, and D is positive 20. If I plug that all in, I get plus or minus 7.11. Now, what's with this plus or minus? This is a situation where the math can only get us so far. As far as math is concerned, this formula has this equation has 2 solutions to it. One of them is positive 7.11, and one of them is negative 7.11. The math isn't wrong about that. But what the math didn't know is what this formula represented for us. For us, this formula was being applied to a sprinter running a race who was speeding up at the last little bit to give her a little more speed going over the finish line. And so while the math might say, hey, this formula has two solutions, positive or negative, we know a little bit more about the problem than our calculator does. So if we're forced to choose between an initial velocity that's forward and an initial velocity that's backwards, in other words, we have to say, does it make more sense that the sprinter would be going forwards at her initial point or backwards at her initial point? Suddenly it becomes obvious that forwards is the clear choice in this problem. So we are going to actually select the correct one from these two, and that's the positive one. So in this situation, our calculator or the math gave us two possible answers. We have to pick the correct one, and we decide that in this case, is the forward option. So, what was her velocity when she started accelerating? 7.11 meters per second forward. There we go. So that's a good introduction on using the big three kinematics equations to solve problems where acceleration is constant. And the problem-solving technique I'd like you guys to sort of practice is writing down the 5 quantities, filling in what you know, what you don't, and what you're looking for, picking a formula, isolating the thing of interest, and then, of course, starting it all off with a quick diagram where, and this is important, you label initial and final. Be clear with yourself about that, and it'll make everything else go smoother from there. That's all for today's lesson.